Good morning. So we are going to talk about something that we tried to test during the COVID time. It's a personalized lung and diaphragmatic protective ventilation. So maybe I think I have a very little conflict of interest because this is pure hypothesis that we have been chasing for years. So the idea is that we have been developing this concept for years. The idea is that I believe, contrary to Martin Tobin, that patient self-inflicted lung injury is a reality, and we have lots of data to prove it. And then we have to avoid excessive effort by the diaphragm. But then at the same time, we know a little bit about the mechanisms of lung injury. We have to avoid some excessive stress on the lung. And at the same time, we know that we cannot promote diaphragmatic atrophy. And then to do this, we have to have a good synchrony because the muscles, they have to work in cooperation with the ventilator. And at the same time, we know already now how much effort of the diaphragm is good for them to keep the trophism of the diaphragm and at the same time to not injure the lung. So the right amount should be something around in between 4 and 12. So we have to avoid insufficient PEEP because this PEEP can change everything here because it can change also the force of the diaphragm because of the Herring-Brauer reflex and also because of the curvature of the diaphragm. So it's very important to measure muscle pressure during assisted mechanical ventilation. During the COVID time, we knew that there is lots of inflammation. The ground glass opacity was typically neutrophil infiltration and edema in the interstitial space. This was proven by many different studies. And then the time in which you have ground glass opacities is the time in which you have lung inflammation. And then it's a fragile parenchyma that has already a first hit. And then your ventilator would be the second hit. So then we thought the general strategy during COVID is first, the patient stays in the bed for a long time. So it's a very long-term general anesthesia, typically 2 or 3 weeks. And then we have two problems. The first problem is that if you are staying in the bed, every one of us, we are going to have atelectasis. And then you have to have a prolonged control of PEEP. And then I believe that PEEP should be guided by the mechanics, not by oxygenation. Maybe we can talk about this later. But at the same time, you have a prolonged inflammation and you have to have a prolonged control of driving pressure. Because it's typically we have a strict control of driving pressure at the first 48 hours, but then we forget about this. And this is the problem with patients with COVID. So, as a general statement, driving pressure is the total pressure that you apply on the system. It's a mixture of what you put on the ventilator and also your diaphragmatic output. And then this is typically underestimated. So we typically underestimate how much the muscle is doing. And for the ventilator, we have always to think, is it possible to eliminate this by using CPAP? Why not? And I typically chase the driving pressure by looking at the tidal volume. Why? Because if I know the compliance of the patient, I can just divide, and then I'm chasing compliance by looking at the tidal volume. I strongly believe that tidal volume is not the target. 6 mL per kilogram is an invention. I think we should target driving pressure, which is a little bit like Michael Pinsky was talking about the driving pressure of all the organs. They are about the same. Driving pressure for all the mammals, they are exactly the same. If you have a little bit more, you are going to have damage. So I think I always try to titrate the pressure support to have the lowest possible tidal volume. Not for comfort and synchrony, because my goal is to decrease lung inflammation in a patient that has very high inflammation caused by COVID. So why we chose to titrate PEEP based on EIT? It's just because there is a convergence of methods in terms of PEEP titration. Whenever you choose the crossing point between collapse and hyperdistension, this x-axis is the PEEP level. It's interesting because now there is multiple studies showing that this gives you 0 to 2 transpulmonary pressure, which is exactly what you have here in this room. It's the typical transpulmonary pressure that every mammal likes. And so we try, the problem is that how to find this transpulmonary pressure in a disease. And I think EIT is a good method. Esophageal pressure would be another option. So in this study, we target, okay, let's see what happens during anesthesia. You have normal lung, so how much PEEP is needed to have this neutral transpulmonary pressure, slightly positive to not have collapse. So we tested this, and then when we didn't put enough PEEP in anesthesia, you can have massive collapse. This was much more than I was expecting. And then if you target almost 0 transpulmonary pressure, you don't have atelectasis after anesthesia. And then let's see how much PEEP in patients. It's much more than we are using. So in our hospital, everyone is using 4 to 5 during anesthesia. And then when we checked this during anesthesia, it's much more, you see, and it's correlated with body mass index. So by this slide, I can understand that we should be targeting different PEEP levels for obese patients. Okay, this is anesthesia, normal lungs. What happens during COVID? About the same. And when I put one on top of each other, I was surprised to see that the difference was just 1 or 2 centimeters of water. How come? The patient is completely, had a terrible oxygenation, but the requirement for PEEP is about the same. Okay, 2 centimeters more. So the conclusion here is that PEEP is much more an anatomical problem, your body composition, the weight of the belly, the shape of the diaphragm, than exactly the lung weight. The lung weight was responsible only for 2 centimeters of water difference. Okay, so we had already this data in our lab, and then we tested this hypothesis that, okay, during COVID time, we tried to set the PEEP at this level, and at the same time, we tried to avoid a high driving pressure. So we randomized patients. So we have almost 40 patients. We selected patients with high driving pressure as a kind of enrichment for this trial. And at the end, we have almost 40 patients in each arm. The control group was the ARDSNet, because I believe that after 20 years, we could not prove that there is a better strategy, unfortunately for me. It's interesting to see that the requirement for, this is the titration according to the ARDSNet, and this is the titration according to this physiological principle. It's not higher or lower. Many patients you have to decrease the PEEP level as compared with the ARDSNet. Many patients you have to increase PEEP if you compare with the ARDSNet. So it's just a different PEEP that is required for the normal physiology. So this is the baseline, no important difference in patients. I call attention that many patients with COVID, they have a very high body mass index. This was a characteristic of the pandemic. So the baseline was 30 to 32. They have a high probability of death, and PF ratio is very low, as you all know, because of the vascular problems. The control group was the ARDSNet protocol, the low PEEP FiO2 table. And then our primary output was outcome. in this trial was the Murray score. I tried to resuscitate this score because I think it's a good physiological parameter to evaluate the lung function. But I call attention that we did some kind of correction in the Murray score to balance the two arms. Why? Because think about let's say, any trial of high PEEP. This is going to cause an imbalance in the Murray score because one group is going to have, by definition, a higher PEEP, or you can change PEEP by FiO2, and because you have a table to correlate both. So you have to do a correction to match the two arms, and then I took all the high PEEP trials and I did a correction based to match. Let me give you an example. So this is the control group in the low PEEP in the alveoli trial. This is the high PEEP in the alveoli trial. So if you take the Murray score, it's going to be higher here because by definition a higher PEEP is a higher score. But then after this correction, they balance. Okay, then I can use this in our trial and check the evolution of the lung function. Okay. How to control the driving pressure? I think we took a serial, let's say, six parameters or six guidelines to decrease driving pressure based on some physiological studies in the past. First this is very easy. So we try to minimize the tidal volume by changing. So I titrate pressure support to have the minimum tidal volume, and I do it in each patient. So then we keep a good pH to not have a very high ventilatory drive, and 7.37 is, in some studies, this is a good parameter to decrease the ventilatory drive. Sometimes if I cannot control the drive, I try to change a little bit PEEP to excitate the Herring-Brauer reflex. This does not work very well. FiO2 is amazing how it works in some patients. Even so, if you target a saturation above 95 in some patients, it's amazing the response. If none of this works, then we give propofol, and as a last resource, we do partial paralysis. How was the result of all of this? First of all, we really could decrease driving pressure in a long range, or in a long period of time. So for the whole patient stay, we could have less 4 centimeters of water in terms of driving pressure. For my surprise, compliance was much better. I liked this because in the early times, in the 90s, the first signal that we had a protective strategy was an improvement in compliance. And then I was very happy to see this. Okay, what happened with the primary outcome? This is the 4 components of the Murray score. Each one of them was a little bit better, including the X-ray, but then we corrected at the end because some people was concerned that, okay, you improved lung function, but what about the rest of the body? So we did some correction for mortality and also for the patient that got out of the ventilator. If the patient dies, the Murray score goes to 5. If the patient is out of the ventilator, the Murray score goes to 0. And then after this correction, both arms, they get to the same value, but you can see that there is a faster recovery of the lung function. And when you model this, it's a very significant difference between the two arms. So you get a much faster recovery of the lung function if you follow these principles. And it's very significant. So the secondary outcomes, I like it very much based on this study. I like very much to follow how long it takes for the patient to decrease the need of supplemental oxygen, because this is a signal that your lung has recovered. So it's important to follow the patient after getting out of the ICU when the patient gets free of oxygen, because this is the real recovery of lung function. So And in this paper of JAMA, we proved that this parameter is associated with a faster delivery from the hospital, discharge from the hospital. And now in this trial, we got the same result. So the patient got out of oxygen much earlier. It's interesting that we could not discharge the patient from the ventilator earlier. There was a trend, but not significant. But we could discharge the patient from oxygen much earlier. And it was 8 days difference. It's a big difference. Mortality was not our primary outcome, but we just checked if there was some side effect. Mortality was equal, and just some physiological exploratory outcomes. I tested this hypothesis: oxygen-free days would be better, and it was. Oxygen-free days is like ventilator-free days. Mortality gets -1, and then how many days the patient is out of oxygen. So there was a big difference. I have more days. Many patients that have many days out of the oxygen. You see this difference, and this was significant. So the difference was 7-1. This parameter now has been used in many different trials. I like this because this is targeting precisely lung function. So instead of ventilator-free days, oxygen-free days, because you are really measuring the lung recovery. I needed less episodes of proning. I'm going to skip this because this is, and then just some safety outcomes. Renal function was the same. It's a concern because we are sometimes increasing PEEP. Mean arterial pressure was the same. Norepinephrine was the same. And now we have something interesting. The propofol use was a little bit higher because I was using propofol to decrease the ventilatory drive. Rocuronium was about the same, except here I see some small difference because we are targeting sometimes partial paralysis to avoid excessive effort. And we used much less fentanyl because we are trying to use propofol instead of opioids to control the drive. Fentanyl does not decrease the ventilatory drive. This is very important. So, the extended lung protection is feasible. This is just a pilot study because we had to stop because of the end of the pandemic. This is just a feasibility study. Due to early stopping, we cannot conclude something in terms of, oh, this is a strategy to follow. It's just a proof of principle. But these positive secondary outcomes, they are very exciting. I think we should test now this type of strategy in a larger trial, or at least testing some components of this strategy in a larger trial, and we did not observe any side effect. Thank you very much.